So what we see here is a schematic small model of a cross-section of a natural area. So what we see here, we could imagine that it is something that covers only a few hundred meters, a few kilometers, or even hundreds of kilometers. So basically what it allows us to see is the third dimension, the dimension we never see when we are walking here on the surface of the ground. What we see here, a layered aquifer with 3 different layers with different materials. So all of them are sands. We have a lowest layer here with very coarse sand, overlain by an impermeable layer that is made up of clay. So it is like a lid on top of this lowest layer, which allows it to be pressurized. Now the top 2 layers consist of medium grain sand and very fine grain sand with some clay lentils in it. Now what we also see here is that we have a few wells and some infrastructure in this area here that go to different depths. So we have a well that is, we could say, almost a shallow well that is just up in the uppermost layer. Then we have a second one going down into the second layer, and the third one that pierces here this clay layer to go down to the very bottom. Exactly the same thing you can see here, where we have again 3 wells going to the different depths, and even another one here. So this is now just the description of the material. But now let's look at the water that is contained in all the pore space of all this material. Very often you will have difficulties imagining that there's a lot of void here, but actually there may be up to 10 to 20% of void space. So there's a lot of water contained in here, which you can actually see by the fact that you have the whole area here is full of water. So in this area here, we can see like a lake, and the water level goes all the way through and is completely stable. It is difficult to see since it's transparent, but we can actually go and look inside each of the wells and see at which altitude the water level is, and we can measure that everywhere, and we will see that it is just a horizontal plane. For water to flow anywhere, we need to get a height difference. So what happens in nature is that we get areas that are higher up, that are called recharge areas. That is where water infiltrates and feeds the groundwater. But we also need discharge areas. That means places where the water goes out. What we do is we create an outlet, which is here represented by a little stream. So now our area, which was a completely flat, here we also have a little lake, as you can see. Okay. So what we can see now, before we had one flat water level all along, and now suddenly we have water up here, and down here. So it is like a cascading area getting lower and lower down. This is what is required in order for water to be flowing. At the moment, when we look how much water is flowing out on this side, we also know that some water is flowing in on this side. And now this would be interesting to now see what happens with the water levels that we just looked at in these different wells. What you can see in this lowest one is actually a water level that is lower than the one that is just next neighboring, and the third one is even higher up. While in these here, we have a high water level here and a water level that is even above the topography in this area here, which is what we call an artesian well, meaning that if we cut this well just at the topography, it will be free-flowing. It will be just coming out. This means that this well here, it is in a confined layer, meaning a pressured layer. This lowest aquifer that we see here, it is actually fed here on the side through a vertical column. So that is where it gets the pressure from. And then the water in here will probably be flowing like this and up there, as we will be seeing afterwards. But how can we see now how the water flows? This is very difficult in an area like this. We know that they are always flowing according to head differences. So if we look at one aquifer, for instance, the one that is drilled into the second layer here and the second layer here, we can see that the difference in head, you have one level up here and the other level here, which is about 1 centimeter lower down. So you can see in the well number 2 that is in this aquifer, you have the water level here, and in this one here, you have it there. Now the difference between the two, this is what will drive the water in this direction from this well to this inside this aquifer layer. Now the funny thing is, you can see in this well here, the water level is lower than here. So what you could imagine, if you don't know anything about what is happening in this area, but knowing that water is flowing from higher level to lower levels, you would get the impression that the water is flowing from this direction to this direction. So that is why it is extremely important to know the depth at which a well has been drilled. So if we want to know how the water flows in this aquifer layer, we have to compare the water level in this well with the water level in this well or in this well. So here, if we compare number 1 with number 6, we will see that we have again a very small difference in height. Why is the height difference smaller in this, for these two wells rather than for these two wells? The reason is that the energy losses in this lower layer are smaller because the material is coarser. So there is less energy that is lost while it is flowing in this direction. To visualize how water is flowing, what we often like to do is that we do something that is called like a tracer test, or it is like artificial pollution, which will allow us to really follow these flow lines. So we will start with the lowest layer here. We will see how it flows, because one thing is just to see the water levels, and one thing is to actually trace it and imagine what would happen with any sort of contaminant that would be arriving down in this layer. So we just inject a color. So you can immediately see a plume created here at the bottom of this well, which is due to the fact that I was injecting a contaminant or a color in this area, and you see it immediately starting to flow in this direction. So now, why doesn't it just stay together like a little spot? Why does it get bigger? Well, it is that actually all the pathways around these grains, there are multiple pathways that have different lengths. So this is what we call dispersion. So the faster this whole plume goes, the more this plume will be elongated. At the same time, you could also see that some of the contaminant actually infiltrated here at the top, which is already contaminating this upper part. So where would we expect this contaminant now to arrive? It is very likely that we will be seeing it appear in this well, but also in this well, and then where would it arrive at the very end? Will it stay down here? No. There's just one way that the water can go from an input to an output. It means if water is flowing here, there's only one place it can come out. So eventually it will have to flow upwards towards this stream. So let's do the same exercise with the second well. I'll take a blue one for this one. Try to do it very nicely. You can see a very dense plume developing just at the bottom of this well. So you can see here now that this plume actually doesn't go straight like this, it doesn't go straight like that, it is actually going in this direction. So it means that flow is always perpendicular to the piezometric lines. It means that if we had to draw now the piezometric lines, they would have to be somehow like this in order to be perpendicular to the flow lines. At the same time, now you can see at the bottom how wide this red plume has become. So it has become, there's some very slow ones here, some very fast ones here, and some of them have already reached this well. So if we now would pump in this well, you will see that some of it will come up. But before we do that, we will even contaminate the third, which is the most shallow one. Let's see. Now that's a very intensive one. So definitely in this area here, we have like almost horizontal flow in this direction because the plume is obviously staying inside this medium-grained sand. Now, it will be interesting to see where this one goes. It obviously has a downward direction at the moment, while the red one at the bottom, you can see it has already, in the meantime, contaminated one of the wells. Now, this is a very interesting thing that can happen, is that you can have two neighbors, one next to the other, and one having a contamination problem and the other one not understanding what is happening. And this can, in some instances, be the reason is that the wells are not drilled to the same depth, which can explain such phenomena. Now, if you look at this last contamination we've just done, you can see it has gone almost very steeply downwards into this medium-grained layer. Why is that? Well, it is a little bit like with everything tries to take the path of the least resistance. So it is being in this fine-grained material, it is there's much more resistance in this fine-grained layer than here. So the pressure distribution forces the water to go down in order then to go along the easier path. Now we can see that this contamination plume here is also starting to arrive, probably also at this neighbor's place. And we can see very nicely now how this red contamination plume is coming up to the stream. So this is an interesting observation that one can make, that you can have a contamination in a far away, remote area, and suddenly you can even get contamination in surface waters or in wells that are far away. So these contaminations that we have looked at just now, this is what we call point contamination. So they are contaminations coming from singular points. What we often have, if we are talking about agriculture or big areas that are contaminated, then we talk about diffuse contamination. So this would be equal to contaminating or coloring now this whole surface to see what happens. This is now the third experiment we are going to do. And for that purpose, again, we are going to take the red. So such contamination can be either agriculture, it can be leaking sewage systems, can be anything that is over a wide area. And you can immediately see the effects where this whole upper area is getting contaminated, close-up surface waters are contaminated. So that is one of the reasons why one often says that shallower wells will have a higher probability of being contaminated, because it's very difficult to protect them from this kind of contamination. So in that sense, when one is looking at drilling a water well, one would always like to find an area where one gets some natural protection, which in this case here would definitely be this lowest aquifer, which is naturally protected by this clay layer. But then again, one has to be very careful. If this well goes into this lower layer, it also means that this well becomes an entry point for contaminations. So that is why it is extremely important to make sure that such wells are extremely nicely sealed in order to avoid any sort of cross-contamination along the well itself. So now we can see very nicely that this last well, which was contaminated or which was affected by the lowest layer, has now a neighboring well which is heavily contaminated by the injection of this second well. And now this well here in the middle is just about to be contaminated by the third. So we can see that the pathways going from one point to the other, they go to different places and they will never cross each other, but they can mix along the boundaries. So this is also what we call dispersion. And again here it is very nice, the movement upwards that one can see. So from the piezometric lines, we would see that the piezometric lines are about vertical in this area here, and then bending upwards in this direction. What shall we do, or how can we decontaminate a well once it is contaminated? Because now we have 3 completely contaminated wells here, and how do we get them cleaned? So a very nice example for such contamination was, for instance, the 2004 tsunami event, where you have a huge wave coming over massive areas and just injecting seawater into all these wells. So what should one do then? Because basically there are 2 possibilities. One is injecting water into a well and diluting, or the other one is pumping it out. Now, each option has its advantages and its disadvantages. Now, the advantage of pumping out the water is, of course, that we remove the contamination. So now I have all my contamination up somewhere, but the very big issue is then to get rid of it and not to re-inject it just next to the well. So this is one big problem that one may get when one actually pumps contaminated water out of a well, is that one has to make sure where to discharge it in order to get it away and not recontaminate an area. So this one here, we will say we've uncontaminated it by pumping. So you can see that by just pumping in here, the well has become very clear, but we have introduced the contamination all over. Now, the second possibility we have is that we can inject clean water in order to dilute and get rid of it. So this is what I'm doing here. The advantage with this is that you get an effect of dilution. The disadvantage with it is, of course, that you keep your contamination down in the underground and it will just continue its way. And if you don't know where it goes, it will still be there. Now, a third option, and that can sometimes be a good option as well, is to do a combination of the two, is to pump and to make sure that it is taken somewhere away, and then add on it some dilution in the end. The problem with pumping is that while you pump, you change the water level. So this was one of the things that happened when wells were decontaminated along the seashore, is that they pumped so much that eventually they got the water from the sea coming in, causing seawater intrusion, which was a worse contamination actually than what they had in the first place. So in some instances, it can be best just to treat and to nicely clean the immediate surroundings of the well and let the dilution of the flow of the water do the rest of the decontamination. So with respect to effects of pumping onto other wells, here we can have a nice example. If we inject or if we pump in this well, which is connected to this well here, if we inject water in this one, you will see that the water is actually coming out of this one here. Why is that? It is, especially in confined aquifers, pressure waves are very fast, are propagated very quickly. So whatever you are doing here will be felt very quickly at the other side. But this is really what you can see in this area here in reaction to the pumping or injecting is just the propagation of the pressure wave and not the propagation of the molecules themselves, which take much longer time, as you saw before with the propagation of the plume. Our last decontamination is now in the downstream area. With this well here. And now it is getting more and more. You can see that the whole contamination in this upper area here is much more diffuse and takes longer time to be evacuated than in this in this lower part. So this model, basically, it allows us to see the most important processes taking place in hydrogeology, and by trying to imagine this model at completely different scales, we can imagine what can happen in all different settings. So just by all the observations we have made now, looking at this model and trying to apply it to different scales, we can see that it is useful, for instance, to have a strategy where to drill a new well. So we've seen that this lowest aquifer here is the best protected under the condition that the wells that are drilled are nicely sealed. But we've also understood how different contamination pathways how contamination can propagate, whether from points or from areas, and how they can go from far upstream to downstream, letting us understand some phenomena that we may not understand by thinking of just understanding that water is flowing from an inlet to an outlet. So it can be applied to all different applications in hydrogeology just by knowing these basic principles.